This video is brought to you by mywayteaching.com.
In the preceding observations, the vector character of momentum has not been evident. In the example so far, we have seen that momentum and change in momentum have the same direction, but this is not the case always. Suppose you just take the stone which is tied to a string like this, and you just rotate it with uniform speed. Suppose a stone is rotated with uniform speed in a horizontal plane by means of a string, the magnitude of momentum is fixed here. So in this particular case, the magnitude of the momentum is fixed. The magnitude of momentum is fixed, but its direction changes. A force is needed to cause this change in momentum vector, and this force is provided by a hand through the string. Experience suggests that a hand needs to exert a greater force if the stone is rotated at greater speed or in a circle of smaller radius, or both. So this corresponds to greater acceleration or equivalently greater rate of change of momentum. So this suggests that greater the change of momentum, greater is the force applied, isn't it? Greater the rate of change in momentum, greater the force applied. So force is necessary for changing the direction of momentum, even its magnitude is constant. So we can feel this while rotating a stone in a horizontal circle with uniform speed by means of a string. So here mass is fixed, means the magnitude of the momentum is fixed, but here the direction is keeps on changing. For that change in direction also we need to apply some force, isn't it? Yes. So these qualitative observations led to the second law of motion, which is expressed by Newton. And Newton's second law says that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Okay. So whenever a rate of change of momentum takes place, that is directly related to the force applied, and always that rate of change of momentum takes place in the direction in which the force is applied. Okay, so thus if under a small action of a force, you just consider under the small action of a force F, okay, for time interval delta t, for time interval delta t, the velocity of a body of mass m changes from v to delta v. So the velocity of a body of mass m changes from v to delta v. Okay. So its initial momentum, we know that it is given by product of mass into velocity. And now it is changes by delta p is equal to mass m into delta v. So according to the second law, so the force is directly proportional to rate of change of momentum, that is given by delta p by delta t. So whenever we change this proportionality into equality, we get a constant, that is F is equal to K into delta P by delta t. Okay, so where k is constant of proportionality. So taking the time limit, that is delta t is equal to 0. So if you take the time limit, that is delta t is equal to 0, or as delta t tends to 0, the term delta p by delta t, it becomes derivative or differential coefficient of p with respect to t. So we can represent that as dp by dt. Okay. So thus we can write f is equal to k into dp by dt. Okay. So for a body of fixed mass, we can consider this derivative coefficient, that is dp by dt, and here the p is the momentum which is given by mass into velocity, isn't it? So we know that the rate of change of velocity is given by acceleration. Okay. So now we can write the second law of motion as F is equal to K into ma, which shows that force is proportional to the product of mass m and acceleration a. So now the unit of force has not been defined so far. In fact, we use equation 2 to define the unit of force. So now let us find the unit of force by choosing the value of k. So now let us take the value of k, we'll assume it as 1. So then we can write F is equal to m into a, that is also equal to dp by dt. So in SI, unit of force is one that causes an acceleration of 1 meter per second to a mass of 1 kg. So that unit is known as 1 Newton. So 1 Newton is nothing but 1 mass, that is 1 kg meter per second square, which means the force that causes an acceleration of 1 meter per second square to a mass of 1 kg. So that entire force is nothing but 1 Newton. Okay. The force which causes an acceleration of 1 meter per second square to a body of mass 1 kg. So let us note at this stage some important points about the second law. Okay. So the first important point is, in the second law, F is equal to 0. If you say the force F is equal to 0, it implies that A is equal to 0. The second law is obviously consistent with the first law, which means when there is no external force, the acceleration which is acting on the body is also 0, isn't it? That is what the first law. So the second law is always consistent with the first law. And the second point is, the second law of motion is a vector law. It is equivalent to three equations, one for each component of the vectors. So the second law is vector law. So we can consider the force Fx as dpx by dt, the three components or the three equations, one for each component of the vector, that is given by max. And similarly, the force in y direction can be written as dpy by dt, that is m into ay, and similarly the force Fz, that is dpz by dt, that is m into az. So this means that if a force is not parallel to the velocity of the body but makes some angle with it changes only the component of velocity along the direction of force. The component of velocity normal to the force remains unchanged. For example, in the motion of a projectile under the vertical gravitational force, the horizontal component of the velocity remains unchanged, isn't it? That is what the second observation point is. So now let us see what is the third observation point. The second law of motion is applicable to a single point particle. The force F in the law stands for the net external force on the particle. So we can apply the second law even to a particle. The force F in the law, what we have just what we have just discussed, it applies. It is nothing but an external force, that to net external force on the particle, and A stands for acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body or even more generally to a system of particles. In that case, F refers to the total external force on the system and A refers to the acceleration of the system as a whole. More precisely, A is the acceleration of the center of mass of the system, about which we shall study in detail. So, this second law, it not only applies for a particle, it also applies for a system of particles with the center of mass m. So any internal forces in the system are not to be included in F, because F is not an internal force, F is an external force. Acceleration at an instant is determined by the force at that instant. The moment after a stone is dropped out of an accelerated train, it has no horizontal acceleration or force if air resistance is neglected. The stone carries no memory of its acceleration with the train a moment ago. So, acceleration is at an instant is determined by the force. You can see here. So the acceleration at an instant is determined by the force at that instant. So the moment after a stone is dropped out of this accelerated train, it has no horizontal acceleration if air resistance is neglected. So the stone carries no memory of its acceleration with the train a moment ago. And the fourth important point is that the second law of motion is a local relation, which means that the force F at a point in space at a certain instant of time is related to A at that point at that instant. So F is related to A. So F is related to A at that instant and at that point. Acceleration here and now is determined by the force here and now, not by any history of the motion of the particle. Okay, so whenever we are determining the acceleration, we'll determine it at that particular instant of time, or which is determined by the force at that time. Okay, it will never, or it will not depend on the any history of the motion of the particle. Okay. So it is determined at that instance by the force at that instance. Okay. In the next part, we are going to solve one more problem based on this.